Okay, now we consider two examples. The first example, the random variable y has normal distribution with the mean eta, which has this form. It's a four-dimensional normal distribution and variance covariance matrix sigma square identity. Here, of course, we can obtain the estimates of the parameters in this way, but in order to be a little bit more clear about that, let's consider the x prime x, b. This is your x. This is your x, and this is your b. And for a moment, suppose that's the first. I use the abbreviation x1 for the first column, abbreviation x2 second, and the third. So x prime xb is equal to a diagonal matrix 4, 2, 2. We have 0 elements. And then the vector of parameters. And also x prime y, in order to write the normal equations, the sum of observations from 1 to 4, you can simply pre-multiply x by y. y1 minus y2, and then the third element you will get y3 minus y4. First of all, note in this design, the rank of a matrix is equal to 3. So it is a full column rank, and the generalized inverse is actually the inverse of a matrix. So the estimator, you can easily obtain it. X prime y, you can easily obtain it by inverting x prime x, pre-multiplying x prime and pre-multiplying y, and after some algebra you will find the estimators. You will get these estimators. Furthermore, look here that all q prime b are estimable in this case. Okay, all functions of the parameters are estimable. But for the inference, we need to compute SSE and SSH. First of all, the SSE, you can easily compute it in this way. The y prime y and this expression, I just add a pen, a page that I can write it clearly here. Remember, the SSE is actually y prime y minus the base estimator x prime y, which you can write it as y prime e prime e inverse e prime y. But here, consider that the rank of the error vector, the error space, the VE, is equal to 4 minus 3, which is equal to 1. So we have one vector E, let's say, it's a basis vector. So we will have one basis vector that can generate the VE. But let's look at this vector. If you remember, the first column is x1. Here first column is x1, x2, and x3. And the condition here must be, okay, this error vector, we should have xi equal to 0 for I equal to 1, 2, 3. So it means that x1 prime e is equal to 0, and then we have e1 plus e2 plus e3 plus e4 equal to 0. x2 prime e equal to 0, so we can get the e1 equal to, we can get e1 minus e2 equal to 0, minus e2 equal to 0, which gives e1 equal to e2. and then x3 prime e equal to 0, which gives e3 minus e4 equal to 0, which gives e3 is equal to e4. For instance, you can take e to have this form. You know, the second elements must be the same, the third the first second elements must be the same, third fourth elements must be the same. So let's take it very simple: 1 1 minus 1 minus 1. And because of that, because we can generate the space of VE with one basis, so I can compute SSE simpler, and I can write it in this way with this E. If I use this E, then you can of course simply obtain it, and the E prime E is equal to 4. So I can write it here. The E prime E is equal to 4, and E prime Y, it means that the first element adding the second element minus third element minus fourth element. So you can write it as this: Y1 plus Y2 minus Y3 minus Y4 squared. So you see, you can get SSE simply in this way, and you can also get it in the form that we wrote above. You can write it in this way. As I said, it's y prime y minus b hat x prime y. So you have x prime y here, you have x prime y here, and if you substitute alpha hat beta hat, you will get this expression. We also need t prime y. Once again, t prime y here in this case is beta hat gamma hat. Beta hat gamma hat. So this is the null hypothesis, and I can write this null hypothesis as this form. So I can write it based on two functions of the parameters. Look here that beta is actually according to b 0 1 0 b, which I want it to be 0, which I can call it q1 prime b, and gamma is 0 0 1 b, which once again we want to be 0, and we can consider it as the second function of parameters. So your q prime is indeed q1 prime q2 prime. Okay, so we can of course get the SSH by this formula. Once again, if I go to the next page, for simple formula, the SSH is given by y prime t prime t inverse t prime y. But once again, I can write it based on this formula ti prime y. Since t1 and t2 are mutually orthogonal to each other, I from 1 to 2, if you take t1 is half 1 minus 1 0 0, and t2 is half 0 0 1 minus 1. So you can easily write it in this form, and simply you can get this SSH. Once again, in order to test this null hypothesis, q prime b equal to 0, from you know, direct way, you can construct your F statistics. It is SSH divided by the degrees of freedom, SSE divided by degrees of freedom. The numerator actually is indeed MSE. It is MSE. Here we have two functions. Since we have two functions of parameters, so we can conclude that S is equal to 2, and here in this case n minus r is equal to 4 minus 3, which is equal to 1. So you can simply write the test statistic in this way. and it has the F distribution with 1 degrees of freedom. But this was the direct way. What about the method of PCE? Let's consider the method of PCE to see how simpler you can get the result. First of all, under the null hypothesis, let's see what happens under the null hypothesis. Under q prime b equal to 0, you will have your vector of parameters as this case, alpha plus gamma and then alpha minus gamma. But in this case, beta is equal to 0, so I can say this one is equal to 0, this one is equal to 0, this one is equal to 0, and this one is also equal to 0. What I get is actually alpha. So under the null hypothesis, your b naught or b0 is just your alpha, and then x is also simplifies, and x naught is just 1. So the expected value is equal to this 1 x naught and this b naught here. Simply we can compute the normal equations. X naught prime x naught b is 1 4-dimensional vector 1 transpose itself alpha, and also x naught transpose y, which is equal to the sum of observations from 1 to 4. But for the SSC, we know that we can write it as you can write SSC as y prime y minus, in this case for the restricted one, remember it is SSE restricted, so in this case I shouldn't write it b hat x prime y, I should write it b naught hat x naught transpose y. Remember, in the original case, when not considering the null hypothesis, on the alternative, in general case, you have b hat x prime y. But under the null hypothesis, your conditional sum square of error is given by this formula, and it is nothing more than y prime y minus 4 alpha hat power 2, because you b naught hat is alpha hat, and your x naught transpose y is 4 alpha hat, so it is 4 alpha hat power 2. And in this case, I can write SSH in this way. So I have SSC, it is y prime y minus 4 alpha hat power 2 minus the original SSA. We have it from above, y prime y minus 4 alpha hat power 2 minus 2 beta hat power 2 minus 2 gamma hat power 2. Here it simplifies, this one also simplifies, and this minus, if I contribute it, I will get the same solution. So it will give the same answer as we considered the common methods. But it was much simpler. Now let's consider another example. In this example, which we already considered in other videos, here we have our x, here this is our x, and here is our b, and if you remember, mu hat was 1/8y1, alpha hat was 1/8y2, beta hat was equal to 0, and gamma hat was equal to 1 over 8 y3. And of course you can write SSE, which we can conclude that SSE is equal to y prime y minus y2 2 once again 1 over 8 y3 2. Now let's consider this null hypothesis, alpha plus beta equal to 0 and gamma equal to 0. I can write it in this formula. It means that under the null hypothesis, the q prime b must be equal to 0. Once again, we need to construct our SSH. The SSH is y prime t prime t inverse t prime y. But we know that this is actually the t prime y. You can easily write it in this way. It is of course alpha hat plus beta hat, and this one is gamma hat, the second row, which I can also write it in this way: 1 over 8 1 1 minus 1 minus 1. I hope I'm not making mistake. 1 1 minus 1 minus 1y, and the other one 1 over 8 1 1 1 1. This one must be minus 1 minus 1 minus 1 and minus 1 y. You see, these two rows are mutually orthogonal, so you can write this based on a simple formula. So I can write it as the sum of ti prime y squared ti prime ti I from 1 to 2. So I can get it better. So after some algebra, you can get it in this way, and we can then construct our f statistic, SSH divided by the degrees of freedom, SSE divided by n minus r. This is the denominator is actually MSE. Remember here we have two functions, so it is q1 prime b, this one is q2 prime b. We have two functional parameters, so s is equal to 2, and in this case n is equal to 8, r is equal to 3, so n minus r is equal to 5. So you can construct your f. Your f is SSH divided by 2 SSE divided by 5, and it has f distribution with 5 degrees of freedom. But we can use the second method. Now let's see the method of principal component conditional error. The method of principal conditional error says that under the null hypothesis, if I go up, I don't want to write it again. Under the null hypothesis, alpha plus beta is equal to 0 and gamma is equal to 0. So this one is 0, this one is 0, this one is 0, this one is 0. If I factorize minus, it is minus alpha plus beta. So alpha plus beta is equal to 0, gamma 0. And if I continue this way, then your design is actually this vector ones. So it is x naught is 1 vector 1 of dimension 8, and your parameter is just mu. So b naught is equal to mu in this case. So similar to the previous example, if you compute x prime, if you write the normal equation by means of writing computing x naught prime x naught b and also x naught prime y, you will get the same answer as the average of observations for the estimate of mu. It is mu, it is nothing than 8 mu, and if I write x naught prime y, it is the sum of observations from 1 to 8. So you can easily get mu hat, which is equal to y bar in this case. Once again, let's consider the SSH. I can use the other page. Let's consider SSH. For your SSH, it is of course the SSC, the conditional error sum of a square. The conditional error sum of a square, you can compute it as mu prime mu. Sorry, it's the sum, the total sum of a square, which is y prime y, minus b naught hat transpose x naught transpose y. But if I go back, first of all, b naught hat is mu hat, and if I compute x naught transpose y, it is nothing more than 8 mu hat. So I can write it as y prime y minus 8 mu hat power 2. Now for the case of SSH, it is equal to SSC. Once again, the sum of a square, the conditional sum of a square of error minus sum of a square of error. This is always greater than this one, so you won't get it equal to 0. Then I can write it as y prime y minus 8 mu hat power 2, and from above we have SSE, y prime y minus 1/8 y2 squared 1/8 y3 squared, and after some algebra you will get this formula. It will give you this formula, and you see the computation has been very simple compared to the usual case. And of course you can then construct your F statistic, and F statistics seems to be the same thing. Okay, the next one is the multiple correlation, which I record another short video in order to save the volume. Thank you.